Okay, now that you're an expert in terpenes and sesquiterpenes, you're ready for cholesterol. Cholesterol, of course, is this big molecule down here. It has 27 carbons, which doesn't sound like a terpene because it's not a 27, it's not a multiple of 5. But it turns out that the way the cholesterol synthesis works, it first makes a molecule with 30 carbons, then it loses 3 carbons. So it's actually 30 is a multiple of 5. And you might think, well, does that start from one big molecule? Well, not exactly, but let's see how this works. But we need 30 carbons altogether. And so if we look at this, we have geranyl pyrophosphate, which makes the terpenes, farnesyl pyrophosphate, which makes the sesquiterpenes, geranyl pyrophosphate makes the diterpenes. Geranyl, they're not getting very imaginative with their names, but we want to go to 30. This just gets us to 20. So how do we get to 30? Well, you might think you take 2 farnesyls and hook them together. Farnesyl pyrophosphate? No, that's not what we call it. But what we do is we use 2 farnesyl pyrophosphates. Now the interesting thing is down here, geranyl pyrophosphate is 2 of these guys hooked what I would call head to tail. Well, for cholesterol, we're going to take 2 farnesyl pyrophosphate, but we're going to do something a little bit weird. Is that it turns out what the way the chemistry works, they don't want to join these things together head to tail. That would actually be pretty easy. But what they want to do is they want to join them together head to head. And how would you join them together head to head? How would you couple these together? What's the problem? Well, the problem is, if you look at this, the pyrophosphate, of course, group is a good leaving group. It's partial negative. This carbon's partial positive. And what we need is a bond between the 2 partial positive atoms. That doesn't make any sense, because if this leaves, it's going to give a cation. If this leaves, it's going to give a cation. How can you hook 2 cations together? How can you form a bond between, well, 2 partial positive atoms before the pyrophosphates leave? Well, what you obviously have to do is you have to reduce one of them. You don't join together a plus and a plus. You need a plus and a minus, right? So we've got to take one of these somewhere now that we're going to have to use a reducing agent. And what's our good reducing agent we're going to use? Well, we're going to use our good old NADPH. And that's going to give us, ultimately, this molecule down here, which is just called squalene. It's 2 of the farnesyl pyrophosphates having lost their phosphates, joined together. But, of course, that needs some reduction. And the molecule we're going to make is called squalene. This is just a pure hydrocarbon, okay? And it certainly looks like a terpene. If you go in, you can certainly find your isoprene units. But its synthesis is really, really pretty wild. And if you numbered the atoms and went from here to there, you'd be surprised because they're not what you think they're going to be. So let's see how this works. It's enzyme catalyzed. 1 hydride is required, 2 electrons to neutralize basically the 2 cations when the pyrophosphates leave. So let's get started. Well, the first thing is you just lose one of the pyrophosphates, form a cation. And then this cation is attacked by the double bond over here. But of course, it's not the N carbon. So we get this intermediate. And you can see already some weird things are happening here because we got this carbon up in the air and we don't want it there. So what happens next? Well, what happens next is the reaction that we saw before, where we have a cyclopropane formed. We saw this back in the first video today in the 3 carene problem. So we pull off that proton, or the enzyme pulls it off, the CH bond attacks the cation over here, and you make a cyclopropyl ring, which still has 1 pyrophosphate attached. And now, what happens next? Well, let's number the atoms, because I told you that if you numbered the atoms regularly, you'd be really weird when you saw we'd be really confused when you saw the final product, and he is. This step itself is weird enough. So what's going to happen here? We still have this leaving group up here. Well, what can kick it out? Well, this is kind of interesting. This cyclopropane just rearranges. This bond swings up and attacks up there. It's actually going to make a new ring because it's going to get a new bond between 1 and 4. Okay, the pyrophosphate is kicked out. Now, why does this work? Well, if the pyrophosphate just left, it would form a primary carbocation. But if you swing up this bond and kick it out, you form an allylic carbocation. And of course, an allylic carbocation is, I don't mean allylic, I'm sorry. it forms a tertiary carbocation. When this swings up, you're forming down here a tertiary carbocation. Sorry, I said allylic. This is confusing enough about me giving you wrong terms. But anyway, this bond swings up, you form a pure cyclopropane now, but you've got this cation over here. And of course, you can just tell some weird things are going to happen here. And what's going to happen here? Well, now we're going to move the double bond over here, okay, form a tertiary carbocation on this side, and kick the cyclopropane open, forming yet another double bond. So we're going to go to this system. This is getting more and more confusing. And look how the atoms down here, the numbers 1, 2, 3, 4. Now they're 1, 4, 3, 2. Is it really smart chemists worked a whole lot of time to work this synthesis out, this biosynthetic pathway out. And they did it by using a lot of isotopic labeling. You can imagine making these things with various carbon-13 atoms here and there to trace this all out. Now we have this cation, and this cation is now going to be where the reduction takes place. This cation is simply reduced by the incoming hydride here from the NADPH, and we go to squalene. So this is a pretty wild synthesis, and we got squalene. Okay, so that was a lot of work. And again, you would never, there's no way that anybody on Earth would have figured this out just by looking at it. It was a whole lot of work by a whole lot of really good people to figure out how this squalene molecule is made in your body. And your body is chugging along making this molecule as we speak. At least I hope it is, otherwise you might be dead. But anyway, yeah, this is the molecule. Okay, so the net result is 2 farnesyl pyrophosphates, a mole of NADPH, proton, and you get squalene. Okay, so now that we got squalene, let's make cholesterol. Now this part is probably the most fun reaction of the entire course. We're going to redraw the molecule like that. All right, now you can see if you didn't know where it was going, no one in their right mind would ever redraw the molecule like this. And so the first step is there's an enzyme that comes along. It's one of these iron enzymes, which is good at oxidations, and it forms an epoxide right there. Okay, now you can almost guess what's going to come. We're going to come along, and all the enzyme is going to do is protonate the epoxide. So when they protonate an epoxide, epoxides open up. So is it going to form a tertiary carbocation or a secondary carbocation? Well, I think it's pretty obvious. For one thing, we know we're going to form a 6-membered ring. So this is all set up for a 6-membered ring, and it's a tertiary carbocation. It certainly looks more stable. Over here, it's secondary, and we'd get a 5-membered ring. So A is certainly what we're going to do. So we're going to form this alcohol with a tertiary carbocation right now here. Now, what's going to happen? Something's happening to this tertiary carbocation. We're going to form a ring. So what happens? Well, this double bond comes and attacks. What would that do? It'd give us a carbocation right there. What can that do? Well, we got a double bond over here. The next double bond can come over and attack. We do again. Now we have a tertiary carbocation there. What can happen? This double bond can come over and attack, form another ring. So now we have a new carbocation. This one's kind of interesting, however. We don't form a tertiary carbocation at this position. It turns out it forms it up here, and which is it's your secondary. But you know, enzymes do what enzymes want to do, and then that double bond attacks the secondary position. Because if it did down here, it would form a 4-membered ring, and that would not be very stable, of course. Then this gives us a final tertiary carbocation up at this position. So going all that work, we get all this. Now the stereochemistry here, of course, is very important. And again, the enzyme is going to pick out one particular isomer, because every one of these chiral centers, you have 2 choices of how you put it together. So what does this tertiary carbocation do? Because we're not done yet. This is still part of the process from opening that epoxide. Well, what is this all set up for? You could say, well, this double bond could swing around. Well, it could perhaps, but that's not what happens. You could find your way to form yet one more ring. But instead, what happens is we have a hydride shift. That gives us a tertiary carbocation there. What does that do? Well, we do a hydride shift, and that moves us one more step. That gives us now a tertiary carbocation there. What does the next one do? Well, we have a methyl shift. Look at that. That gives us a tertiary carbocation down here. Or well, I'm trying to put it down here. What does it do? Well, we do another methyl shift. That gives us a tertiary carbocation there. What happens now? You might think we're on a roll. We're going to do a hydride shift? Well, no, it doesn't do a hydride shift. What it happens instead, the base comes over, plucks off that proton, forms a double bond, and we go to lanosterol. So after all that work, we've made this guy here. Now this thing is a genuine triterpene. It's a C30H50O, so it's a triterpene which has picked up a mole of water. Now, if you try to look for the embedded isoprene units in this, it won't work the proper way because we had that methyl, those methyl shifts in there, 2 methyl shifts. So your basic isoprene framework is not just embedded in this example of a triterpene. Now, this is a genuine steroid. It's the first steroid. It's called lanosterol. And lanosterol is a precursor for a number of different steroids, including cholesterol. So what happens is that another enzyme comes in, and it modifies this guy. And what it does is it basically strips off. So it does some redox chemistry, and it strips off some methyl groups. So these 2 methyl groups down here at the bottom are lost. This methyl group over here is lost, and as you can see, there's double bonds are rearranged. This double bond over here gets reduced. But basically, this is the synthesis of cholesterol. So that's pretty wild. You think I should put this on the test? You do? I don't think so. I'm not going to put this on the test. I know you want me to put it on the test, but I'm not going to put it on the test. So this is cholesterol, though, and it's a good thing to see. And you know, go show when you get out on the town. You know, like sometime, whenever we all get out on the town, show your friends. They'll be terribly impressed when you show them the squalene folding up to form cholesterol. So cheers. See you. When am I going to see you? This is Wednesday. See you Friday.